So we are going to start the first module of the subject Geotechnical Engineering II. So whatever discussed in the course outline, you are already aware of that. So in the first module, we will be covering regarding the stresses developed in the soil, or to be precise, the vertical stress at a point in a soil mass due to various loaded areas. So that will be discussed in detail in this module. So along with that, the problems associated with the determination of stresses. So at the end of this module, you will be able to compute the stress developed, or the vertical stress developed at a point in a soil mass due to applied load on various areas or various shapes over the soil mass. So as written here, stresses and displacements in soil mass is due to various types of loads. Also there is stress in soil due to the self weight of the soil, and those stresses are known as the geostatic stresses. So the stresses which are developed in the soil due to the self weight of the soil, they are called the geostatic stresses. So in Geotechnical Engineering 1, you studied how to find the vertical stress at some depth in a given soil mass. So that is what is the stress due to the self weight actually. So here in the figure you can see this is a plane surface, XY plane, or you can call it as a ground surface, and you have a depth Z in that soil mass. So this is a semi-infinite soil mass, that is, it is confined towards on the horizontal plane, but towards the depth it is infinite. Let us assume that way. So in this plane, as no load is acting on the soil mass on the surface, that means there is no shear stress, as there is no external load. So this is as good as a principal plane. So XY plane is as good as a principal plane. Now you need to find the vertical stress at a depth Z in this soil mass. So what is the vertical stress at depth Z? As we have discussed in the previous version of Geotechnical Engineering, vertical stress is the unit weight of the soil multiplied by that height of the soil. So that is sigma Z is equal to gamma into Z, where gamma is the unit weight of the soil and Z is the height of the soil. So that is the vertical stress at a point Z below the soil mass, or from the surface of the soil mass, due to self weight of the soil. So that's all about the sigma Z. Now from the compatibility equation you have already learned in the solid mechanics and engineering mechanics that sigma x is equal to sigma y is equal to mu by 1 minus mu into sigma z, where mu is the Poisson's ratio, or that can be given as mu by 1 minus mu into gamma z, because sigma z is already gamma into z. So you can write sigma x equal to sigma y equal to k naught gamma z, where k naught is the relation mu by 1 minus mu. So the expression for k naught is mu by 1 minus mu, which is the coefficient of lateral pressure at rest. That is the k naught. This will be coming in further sections where you will be dealing with the retaining walls. So this equation 1 and equation 2 give the stress components at a point in a soil mass due to self weight or unit weight of the soil. Now what are the stresses in soils? So there are two stresses in soils. First one is the, obviously I have already discussed, first one is the stress in soil due to the self weight, and the second one is the stress in soil due to the surface loading. So combining these two stresses will give you the stresses developed in the soil, that is self weight and the surface loading. Now if you take a point in a soil mass at any depth, then that point is represented as a stress tensor. That means it will be represented as a matrix like this. That is, the diagonal elements will be the normal stress components and the off diagonal elements will be the shear stress components. So here you can see sigma x, sigma y and sigma z. These are the diagonal elements, main diagonal elements, which constitute the normal stress components, whereas the off diagonal elements, they form the shear stress components of that stress tensor. So a point which is stressed in a soil mass is always represented by a stress tensor like this, and the corresponding strain tensor is given by this matrix. Epsilon x, epsilon y, epsilon z, they form the main diagonal, that is the strain due to normal stress, and the strain due to the shear strain is the off diagonal elements like half gamma xy, half gamma xz, etc. Gamma here is the shear strain, so don't confuse this gamma with the unit weight of soil. That is a different scenario. Now moving on to the Boussinesq equations. Boussinesq coined equation for stress developed in a soil due to a point load, or you can say concentrated load, in 1885, and the assumption is basically made from the theory of elasticity. He followed the theory of elasticity to compute the stresses developed at a point in a stressed soil mass due to a point load. What are the assumptions made by Boussinesq to formulate the equation? So this is very important. The assumptions made by Boussinesq, it is always asked for university exams as well. So the assumptions are, I will list one by one. First one is, the soil mass is an elastic medium for which the modulus of elasticity E is constant. So that is, he is following the linear elastic theory. The soil mass is an elastic medium. That is the first assumption. The second assumption is, the soil mass is homogeneous. That is, all its constituents, all its constant parts or elements are similar and it has identical properties at every point in it in identical direction. So all the elements of the soil have identical properties in all directions. So that is what is called homogeneous. And next assumption is, the soil mass is isotropic. That is, it has identical elastic properties in all directions through any point. So if you take any point in a soil mass, the elastic properties, the direction will be same. It will be having identical directions for all the elastic properties. So that is the third assumption, that is soil mass is isotropic. And the last assumption is, the soil mass is semi-infinite, that is, it extends infinitely in all directions below a level surface. So take a level surface, as I explained earlier, an xy plane that is confined, then it extends infinitely in all directions below that level surface. So that understanding is what is called a semi-infinite. So these are the assumptions. The first one is the soil is elastic, then soil is elastic medium, then soil is homogeneous, then soil is isotropic, and the last one is that the soil mass is semi-infinite below a level surface. So now consider a level surface. Here you can see a ground surface. This is a ground surface, xy direction is marked, and at the center you are applying the load Q. Capital Q is the load applied at the center, and you need to find the stress at a point P, which is at a radial distance small r, and at a depth z, and the coordinates are xyz for this point P. So you have to find. So how will you find the stress at P, which is at a depth of z from the surface and at a radial distance of r from the center of the loading, that is O, due to this applied point load Q. So the equation given by Boussinesq is the vertical stress at that point sigma z is equal to kb into capital Q by z square, where sigma z is the vertical stress, capital Q is the applied point load, kb is equal to Boussinesq influence factor, and z is equal to depth at which stress is computed. So this is the main equation. Sigma z is equal to kb capital Q by z square, where sigma z is equal to the vertical stress, capital Q is the applied point load, small kb gives the Boussinesq influence factor or the influence of that applied point load, that is indicated by this influence factor kb, then small z, which is the depth at which the stress is computed, and kb is given by the equation 3 by 2 pi into 1 by 1 plus r by z the whole square the whole raised to 5 by 2. So you have to by heart all these expressions. Problems come from these segments, so all these equations have to be by hearted. So the governing equation to find the stress at a point due to a point load is sigma z is equal to 3 by 2 pi into 1 by 1 plus r by z the whole square the whole raised to 5 by 2 into capital Q by z square, where this expression, this entire expression is the influence factor kb, or we call it precisely the Boussinesq influence factor. Capital Q is the applied point load and z is the depth at which you are computing the vertical stress. So this is a dimensionless quantity. The kb is a dimensionless quantity, and if the stress applied, if the load applied is in kilonewton and you have z in meters, the depth in meters, then the unit is like sigma z is expressed in terms of kilonewton per meter square or kPa. Now what about the intensity of vertical stress directly below the point load Q? So here in this figure you can see, now I have considered a point P which is at a radial distance small r from the center where the load is acting. Now if I am considering a point directly below this load, then this r becomes 0. So in the equation of sigma z, you substitute the value r as 0. So in this equation of sigma z, you keep r 0, then you get this expression. Sigma z is equal to 0.4775 by z square into Q. So this is the expression for vertical stress at a point directly below the point load. Next is pressure distribution diagram. So there are different ways you can represent the pressure distribution in a soil mass. So first one is the stress isobar or the isobar diagram. The second one is the vertical pressure distribution on a horizontal plane, and the last one is vertical pressure distribution on a vertical line. So last two, as far as syllabus is concerned, not that important, but you must understand that aspect as you move forward in the remaining sections. So the first one is very important, always ask for university as well, stress isobar or isobar diagram. So the isobar part is very important as far as exam point of view is concerned. So what is an isobar? So isobar is a curve or contour connecting all points below the ground surface of equal vertical pressure. So when a load is applied on a soil mass on the surface, below the surface, within the soil mass, isobar is that curve which joins all the points which is having the equal vertical stress. That is, if for all the points we are having the same stress. So you keep on connecting all those points to form the isobar. So it is a spatial curve of the shape of a bulb. So it is like a bulb. The isobar is like a bulb, or you call it as an influence. That is the zone of pressure. So that is the zone of a given pressure. So if the pressure is like say 0.25 Q, or if Q is the applied load, then that you have an isobar for that 0.25 Q. I will go into detail. So now why it is having the shape of a bulb? Because the vertical pressure on the given horizontal plane is the same in all direction at point located at equal radial distance around the axis of the load. So you keep on take the radial distances, and for all the you take the radial distance where that stress is same, and that all the points are joined together to form the isobar. Now what is the pressure bulb? The zone in a loaded soil mass bound by an isobar of given vertical pressure intensity is called a pressure bulb. So this is what I mentioned earlier. So you plot all the points, all the curves having equal vertical stress, and then you joined all those points to get a bulb. So for a given stress intensity, this bulb is the zone for that given stress intensity. So that bulb is called the pressure bulb. So if the stress intensity is Q, then for Q there is a pressure bulb. If the stress intensity is like 0.25 Q, it has another pressure bulb. And keep one thing in mind, Q is the load acting, total load. So you take it in, if it is stress, you take it in terms of Q per unit area. So for every stress you have a pressure bulb, and obviously for Q, that is Q per unit area, will be having the highest magnitude, and as you go down the stress intensity will reduce, like 0.5 Q, 0.25 Q, and so on. So with depth the stress intensity will reduce, also with radial distance the stress intensity will reduce. So with the help of pressure bulb you can say that what is the influence for that applied load, and that is the main application, field application of this pressure bulb. Now let us see how we will plot an isobar of sigma z is equal to 0.25 Q per unit area. So I am just considering a random case where the vertical stress sigma z is 0.25 times capital Q per unit area. So you already know the equation for sigma z is equal to Kb into Q by Z square. So now I take Kb in terms of sigma z. So Kb is equal to sigma z into Z square by Q. You already know what is sigma z. I have taken here assumed as 0.25 Q. So substitute that here, 0.25 Q by Q into sigma into Z square. So you get Kb is equal to 0.25 Z square. So what is the extent to which this pressure bulb will go, or what is the depth to which this pressure bulb will go? So if you are given a sigma z, say here I am considering sigma z is equal to 0.25 Q per unit area, then if the r is 0, small r is 0, then you have the Kb value as 0.4775. Now you already have the Kb as 0.25 Z square, which I have explained earlier. So from that you can find the Z value, that is 1.38 units. Here I am not mentioning the whether it is in meter or centimeter, so it is units. So here the small z value is 1.38. So that is the depth of the pressure bulb. That pressure bulb will extend only to that depth. It won't go beyond that depth. So you can fix the depth of the pressure bulb by substituting the value r equal to 0. So depth is fixed. Now you keep on increasing the value of z, that from z 0 to 0.2, 0.4, 0.6, so on. You keep on increasing the value of z till that depth, that is 1.38, and correspondingly you find what is the value of the Kb. Okay, so how will you do that? So here is the computation. You have z, you increase it from 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.38, and then corresponding to that you find Kb. What is the equation for Kb? Kb is equal to 0.25 into Z square. Substitute the value of Z here. You find the Kb value till 1.38. 1.38 Kb value we already know, it is 0.4775. Now if you know the Kb value, you can definitely find the R by Z from the Kb equation. So you get the equation. This is the equation for Kb. 3 by 2 pi into 1 by 1 plus R by Z whole square raised to 5 by 2. So you have Kb. From that you find the R by Z. So you have the R by Z. Already you have taken the Z. So from that R by Z and Z, you get the R value. So you have the depth 0.2, 0.4, 0.6 like that. You have the radial distance 0.38, 0.52, 0.58, 0.59 like that. Now you plot the isobar. So you have on the X, you will be plotting the radial distance R, and on the Y downward direction you will be plotting the Z, and you will compute, you will mark the points. So what is for 0.2 corresponding to 0.2, what is radial distance? It is 0.38. So you mark that value 0.38. Corresponding to 0.4 Z, what is the R value? 0.58. You mark 0.58. So like that you mark up to point. For R0, what is the Z? It is 1.38, or vice versa. For Z 1.38, R is 0. So let us consider this point as Z is equal to 1.38, where R is 0. And you complete the entire plot. So this will be the isobar, or this will be the pressure bulb for that particular load intensity of 0.25 cube per unit area. There are more cases of pressure bulbs and also the limit for various cases of loading. I will be while discussing that part, I will be in detail, I will give an idea about the pressure bulb. So saying about isobar is symmetric about the axis of loading. So here you can see this is the axis of loading. You are applying a load Q. So this is the axis of loading, and the isobar is always symmetric to this axis of loading. So that's all for now. So in the next class we will be discussing about the vertical pressure distribution or stress distribution on horizontal plane and vertical line. Okay.